Hi everybody, thanks for coming to my talk today. So my name is Bot on the internet. In the past I've written computer viruses. In 2019 I made some friends online and we started this cool little malware collection that eventually became VX Underground. I created the Black Mass magazine for VX Underground. I worked on a decentralized, a peer-to-peer anonymous publication system called Freenet. We've taught classes about rootkit design from userland all the way down to firmware. And my day job is that I'm a security engineer, currently Wink. So that's a little bit about who I am. Since I am employed, I have to tell you that, my employer doesn't think any of the things that I'm about to say, which is, I'm about to get a little bit spicy, so I guess that's a little bit important or whatever. But yes, if you know who I work for, then they don't mean anything by what I'm about to say. Okay, so some people have dreams, and while I do have dreams as well, I also have a whole lot of nightmares. In 2021, something occurred to me. Essentially, the direction of the tech economy, even at the time, was such that things were already being, kind of consolidated into a cloud environment, and that has deeper implications, even social implications, than I think a lot of people realize. This was, of course, before the LLM explosion and all of that stuff, which only amplified what eventually, I think is slowly becoming a reality here. But essentially, I had a concern that over time, what we now call AI would be used to assist, not just to do good things, but also to monitor and watch us at all times. There are authoritarian governments. I would call today's Russia authoritarian. I would also call today's China authoritarian. That, in both of these countries, there's what has essentially become a national digital ID. In some cases, you have to use it just to get on the internet. Applications, private conversations, are essentially being banned or are banned in these countries. So, like everybody thinks, well, oh, WhatsApp is banned in Russia because, they want to be able to read everyone's messages. That's definitely true. And some people in the audience may be familiar with WeChat, but now Russia has their own, essentially WeChat-esque system called Max. The whole purpose is very obviously to watch everything everyone does and says, right? So if you add AI to this mix, it's not hard to understand what an absolute complete nightmare that could become. And we tell ourselves that we're better. We tell ourselves, oh, we would never do such a thing. But that's not what we're seeing, right? What we're seeing is Larry Ellison, very famous billionaire who owns Oracle, was enthusiastically speaking about the use of AI in basically civic government, and the quote was something along the lines of, well, police will be on their best behavior because everything will be monitored, and citizens will be on their best behavior because everything is monitored, which is either an incredibly naive thing to say or an incredibly cynical thing to say. I'm still trying to figure out which one of those were. And then obviously Europe is legalizing or attempting to legalize basically constant surveillance through their own laws. So this bothers me a whole lot. It's definitely something I think about. It's something I've been thinking about for a long time. But there's a thought that I keep coming back to, which is that sufficiently advanced privacy tech is indistinguishable from malware. And this is essentially the crux of the idea that I'm going to arrive at here. So if somebody inside of a hostile environment has some software in their computer that could be identified as malware, but they actually use for, again, if they for example, live under an authoritarian government and would like to speak to their friends without constantly being monitored. It provides sort of a gray area or plausible deniability if that happens to matter in that circumstance. So with all of that being in mind, that is essentially the motivation for what I'm about to show. So yeah. The first part of it, again, I published an article on this 4 years ago somehow, essentially detailing, okay, well, intelligence, if we define it broadly, is essentially problem-solving ability. When people think about AI, they think about, largely at least, they think about how can I make an intelligent system most like a human. But humans evolved a specific way where we can be aware of certain things and not others. There are things we're good at and things we're very bad, types of reasoning we're awful at. So I wanted to explore the concept of an intelligent swarm, because if there's going to be like a centralized super AI that watches everything, then it would also be in our best interest to have sort of like a counterbalance, right? So if you've got a computer virus that provides plausible deniability, it has to be able to adapt. There's just no way around it in this sort of nightmare scenario. So I'm going to dive a little bit into how that works. That's all been published. The source code for that is in that QR code if you want to take a look. And I'll have more resources at the end. But that's essentially the foundation for the idea that I'm presenting today. So I am creating a peer-to-peer botnet called Dendrite that essentially leverages the initial idea of swarm intelligence. And we need to create something that can reasonably adapt and fight back against, sort of all-seeing and an environment that's heavily monitored. So what characteristics should this software have? Well, as I mentioned, there's the whole swarm idea, which I'll get into. But it should also be self-modifying, and not just in the way that people are used to self-modifying code. In most cases, self-modifying means, okay, well, I replace certain specific instructions, or I, change, maybe some strings get encrypted with a different key or something like that. That is not at all what I mean. What I mean is the code needs to discover logic that it can then actually use in the real world. Ideally, that's step number one. It is a lofty goal, but that's step number one. Ideally, much more is possible. But how would we actually design a system like this, right? Because at this point, it still feels very science fiction. So, what characteristics would this software need to have? Well, if you're using AI, you can't just load up, a 12 gig LLM in memory and expect that no one's ever going to see that. It has to be low resources, and it still has to do its job. There can't be a single point such that you could disable the entire thing. If a network is discovered, it has to be resilient against, well, it should be resilient against discovery itself, but also direct attack. It should be self-improving, and again, there should be some kind of collective reasoning. How that works can actually vary. So what is our solution? We're going to make a peer-to-peer network that evolves code. So the thing about, I'm going to get into the details of how our overlay is going to work. But what you need to understand about peer-to-peer networks in general is that the programmer's hammer for creating peer-to-peer networks is what's called distributed hash tables. This is a well-studied and well-solved area. The problem is that, so although these are very efficient, they're often, essentially just used for storage and retrieval. BitTorrent is an example of oh, I'm going to use this overlay network to retrieve data. You know, maybe it's a movie, maybe it's a Debian image. It doesn't really matter. But what if we can use a distributed hash table for something else entirely, like compute or managing bandwidth in a distributed way, or, I don't know, code evolution? So as I mentioned, they're very traditional DHTs are super efficient, but the problem is that they're really, really easy to attack. Essentially, what you do to attack a vanilla DHT is you find if there's a tracker, you're in good hands. But you can request peers from the tracker, and then from the peers, you request more peers. The next thing you know, you have a full or a very good map of the network. This is actually how a lot of malicious botnets are taken down, is by querying the DHT, getting all the nodes, and then you discover some issue with the malware. It's often very hastily written, and it's really not that hard to. In general, actually, a distributed hash table is not that difficult to disrupt.
What are you trying to do in terms of disrupting it? Are you trying to create like false matches? Are you trying to enumerate what the source of the hash is for the members of the network?
Yeah, absolutely. So it opens up there are two angles. One is straight up just monitoring and denial of service for individual hosts. Distributed hash tables also have the concept of supernodes, where they're not necessarily a tracker per se, but they're one that everybody goes to get additional connectivity. So there's the denial of service angle, but there is also being able to freely join a peer-to-peer network like this does, in many cases, introduce a direct vulnerability, because the model that the programmer used to insert data into the network often has issues. For example, at the application layer, they're often not checking if something was correctly signed. They're not checking the actual hash of it. They're just saying, oh, this is a command. It belongs in the hash table. Here's the associated result with this command. Anybody, but what they're not getting is that often all of this stuff can be messed with, and that's not even getting into authentication systems they have and things like that. So I would say that the two angles are the denial of service aspect, and then just anybody freely being able to join a network of that type, I would say can itself be a vulnerability. So what's our solution? There's a well-studied type of network that is just based on how humans socialize, called a small world network. Stanley Milgram in the 1950s studied this very well. You've heard of the 6 degrees of separation. That actually, fun fact, was an estimation for the population of the United States at the time. So that was for about 150 million people. And that's actually not, globally it's not 6, I'm just saying. Anyway. But the nice thing about human social networks is that they almost never, it's very rare to have a social network that strictly relies on one person. It's not impossible, but it's that essentially doesn't happen. If you think about a human social network, when you remove people from it, it often adapts. Rumors spread very quickly. And so the nice thing is there's no central control, information flows very freely, and it's hard to disrupt. So, let's see. So the question being essentially, what if a computer network works this way? What if a computer network functions the same way that people socialize? And just to be clear, small world networks aren't just how humans socialize, they also occur in nature. Like your short-term memory actually has the structure of a small world network. So for the other beauty, in my opinion, of small world networks is that only a small number of connections per node is required, and you often don't need any new ones. It's very robust that way. The other thing I wanted to point out, if you look, so what you'll notice about this graph the general structure of a small world network is such that you'll notice that the nodes that are closest, there are more connections per node to the ones that are closest to each other. And then you'll notice there are fewer long lengths. So a higher proportion of close connections, and then a still existent but lower probability of like longer distance connections. This actually forms a very efficient structure. Let's see. In simulations, I was able to rip out randomly 33% of the network, and it ended up in about a between 10 and 15% traffic loss, which I think is pretty good for not having a tracker, not needing to ask for new peers. I think that's pretty good. The other nice thing about, so this creates what is called a restricted route network. And that's exactly what it sounds like. So if a computer only needs to make contact with 2 or 3 other computers to efficiently search the entire network, what can easily happen is if you're in an environment with restricted connectivity, like for example, if you're inside of maybe like, if you're inside of Russia, for example, and you want to just visit a banned website, obviously there are practical ways to do this, but you could, for example, use a restricted route peer-to-peer network to very stealthily fetch the content that you wanted, have it relayed back to you via peers, and it would be pretty hard to figure out because you can't just randomly connect to a node in this network. In fact, it's very hard to pick a random one and identify it. You would essentially have to traverse the entire network to identify every single node. And the only way really to do that would probably be to be an ISP or the NSA or something like that. Okay, so but practically, how does this actually work? There's a guy named Oscar Sandberg in 2006 who did the math essentially that allows a network of this type, again, that doesn't have to ask for new peers essentially, to have an efficient small world topology. The idea summarized essentially is in a virtual addressing space to calculate the mean distance from a randomly selected neighbor to their neighbors versus your distance to yourself. And if you are closer to your peers' neighbors than yourself, you can propose a swap in the virtual addressing space. And you're now both closer actually to a small world distribution in the virtual addressing space. So, what does this mean? It means that you end up with a topology that with no tracker or anything, has a log n squared search performance, which, if you think about it, is pretty good. So, I think it's like, so for 1,000 nodes, that'd be 9 hops to efficiently find like everything you would need. Okay, so that's the network foundation of how a botnet like this would function, right? But I mentioned a few characteristics. One being the network itself, but 2, evolving code, which is kind of the loftier goal here. So I weighed many, many different options. I looked at all different types of lower compute AI to actually accomplish this goal. One of them being called SOAR cognitive framework, very robust, very useful, but ultimately very complicated and computationally expensive. What does produce results is genetic programming. So in genetic programming, if you're not familiar, essentially you create a fitness function for something that you want the algorithm to discover. This essentially defines what you're asking for. And then you essentially use a set of methods or operations in some function domain to achieve that goal. The way this really works is that there is essentially an abstraction created called a genome, which operations are then done on. So in genetic programming, you have genomes, which is, for example, a computer program, and you have individuals, which are essentially candidate programs for your solution. You mutate them, and you go through a selection process. So an important thing to understand is the fitness function will absolutely 100% define the entire effectiveness of whatever you're trying to create. So you have to be sure that the exact things that you specify end up, like in all conditions, end up being what you want. The other thing is that you can't just select candidates based on their fitness. If you do this, all candidates will converge on a solution that's suboptimal and too quickly. So actually you have to balance diversity of genomes with fitness. If you only pick the fittest individuals, then you're going to converge too quickly and you'll never actually get there. And obviously if you only pick, the most random individuals, you'll never have like fit solutions. So what you have to do is decide like which proportion you want. Okay, so I've done a whole lot of yapping, right? But I just wanted to demonstrate an evolutionary algorithm working in a very simple way here. One moment. Great, okay. So this is a simple demo where we just start with string. Let's see, is that too small? Do people read that?
No.
No? Okay, 1 second.
There's no smoking in here.
Sorry.
No snitching either.
Okay, cool. I have a solution. One moment. It's there we go. Okay. So this very simple, easy demo just takes it takes 1,000 individuals of random strings. What you'll see is okay, so very simple demo, but effectively you start with random noise and there's a desired outcome that we're trying to get to. So with every generation, the measure that we use, I'll go back to showing the IDE now. The fitness function essentially measures the closeness of the newly generated string. It creates a score based on position and the lettering again, in this very simple case of how close or how fit that individual is. So that's a simple example of a string evolving, but of course we would like to do something more advanced than that. Okay, so with this approach, right, it is kind of crazy that it actually works, but it's really slow. And like, how would you actually do this with computer programs, right? Like, isn't that a huge problem? Like, you can't just randomly mutate instructions, can you? Right? Like, that's like, how could that even work? Okay, well, actually somebody figured this out already. In 2010, there's this guy named Lee Spector who kind of sounds like a superhero. And his solution to this problem effectively was to create a VM. It's a VM that evolves programs. It's a stack machine, but not in the way that you would think of a normal stack machine. In this machine, every type of data has its own stack. What this allows is it allows the VM to be tolerant to bad instructions. So if I put a bad instruction on the exec stack and the corresponding types are not in their stacks, are not available, the VM just no-ops. It just basically skips it. And this trick, although incredibly simple, ends up like, it appears to me at least, completely fixing this problem, which is kind of a big deal. But the other nice thing about PushGP is that it's intended to be modified. So it's intended to have instructions that correspond to anything, like method calls. So you can do, you can go from, writing cute little instructions in the spirit of Core Wars to actually doing stuff in the real world, evolving against stuff that programs that run on your computer already. So when you make this balance of mapping special instructions that you created with the ones that are already available, you can reduce the search space of your genetic algorithm and make it way, way more efficient than it would normally be. So in the PushGP VM, individuals obviously are sets of instructions. There's an instruction for every data type, and the exec stack itself can also operate on itself, which is kind of cool. All right, let's get to a practical example now. Sorry, I know it's a lot of background, but like, there's a lot to it. So let's say that we wanted to like evolve our own obfuscation for our code, right? Well, what would we need to maximize? In this example, we could maximize stack junk. We want, like, conditionals are always fun to throw in, and of course it should be like long, right? So that's what we're going for. Correct, yes, and it does depend on the score that you're aiming for. So in many cases, you're optimizing toward 0. Actually, it's kind of counterintuitive, but you want, yeah. I'm so sorry. I just need 1 second here to make this bigger. Great. Thanks for bearing with me. Is this readable? Yes. Great. Okay. Okay. So you'll notice that happened very quickly. But effectively what's happened here is that based on these constraints, scroll up just a bit, based on these constraints, we had, the task is essentially to pop all the integers off of the stack with a set of obfuscated instructions. And this was just a random run, but what you'll notice is the PushGP VM created a set of instructions that effectively resulted in no-op, the longest chain of effectively no-op instructions it could find for itself that would also accomplish the goal of popping 1, 2, 3, 4, 5 off the stack, right? So what you can do, so first of all, that actually worked, which blew my mind when that happened. But you now have the ability to, in a obviously like very low compute way, evolve functional code. Okay, so I just demonstrated very simple code obfuscation example, but there are many more possibilities than this. One that I'm currently working on is network protocol side channels. So taking an arbitrary protocol and creating valid traffic that can hide information inside it without disrupting the actual function of the code. I already did the code obfuscation one, but another, the ultimate goal, or one of the ultimate goals here, is to have the network do distributed vulnerability research, with the idea being that upon success, a new vulnerability would be discovered and then distributed to the rest of the network and then used, and then continue to use that to spread. And then, so the question remains, like, how do we actually make a swarm of computers do this without like close management and monitoring? In the virtual addressing space, effectively you can use that as you can use the limits of a node's responsibility in that space as a partition. And you can just map the inputs directly to the virtual addressing space. And then you effectively have a large, it's like you have a large distributed compute cluster, essentially, that will evolve code for you. And then some more future work is I'd like to make the network sense things based off of what data it can collect and then make decisions on that. I sort of alluded to this already, but I would like to be able to create this idea of pluggable transports where you can just take any protocol, any system that's convenient for you or not being closely monitored, and use and adapt that. I have a lot of goals for this, and actually quite soon I'm going to have a whole bunch of free time. So yeah, that's essentially where it's at currently. So 2 resources for you. One is my Twitter if you want it, but the other one is all of the VX Underground Black Mass copies, which fully describes the peer-to-peer network. And as I mentioned, the source code for the peer-to-peer network is in this slide. So that's where that source code is. Wait till everyone's done there. Okay, that is where it's currently at. Does anyone have questions?
The initial testing that you were doing with trying to obfuscate like protocol communications, is it just resemble something like substitution or very strong obfuscation, or was there anything that sort of resembled encryption itself?
That's a great question. And I think in the right circumstances, it can kind of converge on that. The solution that the thing that I observed was just like how the experiment I did along those lines was just regular TCP, and it was just essentially, it was discovering what fields or what data can I insert without harming this TCP packet. It was kind of very basic, but actually, to your point though, genetic algorithms, they don't care at all how they get there. And that actually makes them perfect for like nonlinear solutions that are very hard to understand, for humans to understand. And mathematicians would certainly not call it encryption, but you can definitely have genetic algorithms that create solutions that are that one, reliably work, but 2, are so complex that most humans would take a very long time to understand it. Yep. Okay. Sorry?
That was awesome.
Oh, yes.
Somebody's asking to go back to the QR code.
Oh, sure. Which one of these?
That one.
Okay.
maybe a bit similar to the previous question, but on the regards of auto generation evolution of
I'm so sorry, I actually can't hear you.
yes. So for the matter of genetic programming on network protocols, forgive me if this is similar to the last question.
Sure.
Is it a matter of kind of, you said there's a little bit of templating in that, I felt like. So is the capability for evolution of protocols in the big picture of things? So is the evolution of how to actually have the botnet communicate in terms of just substituting out, like, let's say, like a packet kind of structure for things in the model, or is it more overarching that? So for example, you were talking about if there were multiple PvP, other protocols, would it be able to dynamically expand that domain?
Yes, absolutely. 100%.
It's a bit more complicated to get one than versus the other. I was wondering if you had any insights on that.
Absolutely. So you could 100% do that. You would use custom instructions, and those custom instructions wouldn't be hard to make. It would essentially be, hey, I'm calling a method that generates this frame, or I'm calling a method that generates this traffic, even this stream of traffic. Like you can go from packet to like a whole stream. There's no limitation on that, and yes, you absolutely can do that. Yep.
But the other use case that's more for obfuscating code, like for malware, would it be possible? I know that you were demonstrating using like the genetic model and that VM, but is it possible to also inject like additional training data to make it smarter at doing that, or the whole point is that that is unnecessary and it does it absent that?
I love that question. That's a great question. So in the sort of model of you have some surveillance system, the way I was sort of thinking about it was, okay, well, what happens with malware in the real world? They discover how C2 works. They make signatures against it. And often it doesn't take that big of a change to break that. And that sometimes applies with obfuscation as well. But I think the bigger part of your question is like, oh, well, could I make it more complex, or could I introduce other factors? There is no reason you couldn't do that. And you probably should, honestly. This has been, for me, a project I've just been working on in my spare time over the last probably like 6 months-ish, but, or I guess closer to a year, but there are so many possibilities. Like, there's a lot, and I think it's very underrated. I think the thing that makes me so interested in this is how quickly that ran and the fact that it actually works. I think it's very promising, yeah.
What were some of the other algorithms you tried?
So I tried, I was very satisfied after I started doing genetic programming. I did try SOAR, which is a combination of, there's short-term, I forgot what it's called. It's basically short-term learning and reinforcement learning. And with SOAR, what you do is you provide a set of steps, and you say, these are the actions you can possibly take, and then it essentially uses a combination of situational learning and like reinforcement learning to figure out how to achieve its goal. It is smarter. It's better suited for very complex problems, but the footprint is number one, the footprint's quite heavy, and number two, it's very complex to use. So I kind of didn't go with that one. But as soon as I tried genetic programming and it worked as effectively as it did, I decided I was satisfied with that.
All right.
Cool.
Awesome. Thank you very much.
Thank you.